This video will continue our discussion of limits of vector value functions. This is going to be talking about continuity. We did a definition in continuity in Calc 1. The definition, it had to meet three things. I'm going to do it in vectors, or sorry, in functions. It was that f of c, so we're talking about is it continuous at a point of c, that we wanted this to exist. We also wanted the limit as we approach that function at that point to exist. And then the last point was that those two things are actually the same thing. This made sense. Let's draw a picture real quick. If I have a graph and here's C, then I want my function to exist at that point, but I also want the curve to exist at that point. What that means is they don't want it to be like this. They don't want some point up here, and then the curve actually runs through here. And then remember, the definition of continuous is I can graph it without ever lifting my pencil. Well, this graph that I just drew satisfies that. It exists. It's this point. It also satisfies this. The limit exists, right? They approach the same thing, but they are not equal. That was the definition of continuity. We could run through this list, but actually with vector value functions, what we get is as long as we are giving three things and we look at the domain, where it's going to be continuous will be on its domain. I'm not going to get too much into theory. I debated there for a moment how far I wanted to go into it. I would maybe recommend reading some of those paragraphs out of the book. It's not something I'm going to focus too hard on, but it is good practice to find our domain again. Okay, so if I find the domain of a vectored value function, it is continuous on that domain. So I'm going to write that here. It is continuous on domain. So all I have to do is find the domain. So let's label these x of t, y of t, and z of t. The domain of x of t is equal to all t's such that, and then just t can't be 0. Right? The t, I can plug whatever I want into cosine. Any t will work. But I can't divide by 0, so that eliminates the bottom. Okay, y of t is a little more complicated. We have a couple things. I know that the square root makes it where it has to be non-negative, so it's going to be 0 on. But we also have this. That can't be 0. So if I think about when will that be 0, I'm just solving. So t equals negative 1/2 would be when that is a 0. That's not even in the domain of this. This is t's greater than or equal to 0. So the negative 1/2 is not even included. So these are all t's such that t is greater than or equal to 0. Right? And then the domain of z will be all t's such that, and then I can times t by anything. The t's in the denominator are my exponent, so t cannot be 0. All right, so the domain for all three, or the vector value function rather, would be the overlap of those. So this is going to be all t such that, okay, where the overlap, it can't be 0, it has to be greater than 0, so it's all t's greater than 0. That implies that r of t is continuous on 0 to infinity. All right, so it's the same as the domain. If you find the domain, you have the interval which it is continuous on. All right, let's do one more, just for more practice for finding domain. So continuity, again, is continuous on its domain, so all I got to do is find the domain. I'm going to label each one of these, x of t, y of t, z of t. All right, so this one's going to be a bit tricky. Domain is fine on the first one. All right, domain, if you notice, t can't be 2 and t can't be negative 2. So we're going to say all t's such that t can't be plus or minus 2. Can be anything else, though. The domain of y of t, or all t such that, okay, now the input for this is a inverse sine. So everything we're going to plug in here will be the range of sine. So it's like the opposite, right? Sine, I can plug whatever I want into sine. And then if you're thinking about sine, the domain of sine goes, range goes up and down. It is caught between -1 and 1. So the domain, or sorry, the range of sine, there's range of sine, let's put this down here, equals the domain of sine inverse. It's the opposite. So if the range of sine is -1 to 1, the domain of inverse sine is -1 to 1. So I'm going to say negative, we should say what this is where t is. So I'll use that little fancy symbol again, -1 to 1. And then we have one more, domain of the cube root, which is z of t. That could be anything. So now to find the domain of my vectored value function, I'll do all real numbers here. It's the overlap of all three. So the domain of r of t is the overlap. Okay, we got -1 to 1 is limited for this one. So that takes care of this if I just use that one. And then cutting out +2 or -2, they're not in there. So the domain would be, let's write this formally, all t such that t is an element of -1 to 1. So there's my domain, which implies that r of t is continuous on -1 to 1. Okay, so hopefully this domain stuff's coming back. Like I said in a previous video, I know as a student I brushed by it every time, which is fine. You can get by, you can make the grades. But at some point I was like, oh, I actually need to understand domain and range, because that is one of the most important parts of your application sciences later, is that you're going to be applying your X, Y, and Z, your inputs. You're going to be applying with models. Sorry, I lost my train of thought there. But you're going to be applying with models, so it's going to be very important what you plug in and what you don't plug in.